Welcome to this tutorial on docking ligands with PyRX. I'm doing this tutorial in Mac Yosemite, so that's actually operating system X10.10.5, and I'll be using a number of software tools. One of those tools is Google Chrome, and I'll take that right to the Protein Data Bank website, and we'll come back to that in a moment. I'm also going to launch PyRX, and PyRX is actually the tool that will enable us to do the docking. PyRX contains a number of interesting and useful tools in it. One of them is Autodock Vina, which contains a scoring function for how well things bind together. And so this is the PyRX interface that's coming up here, and we will be using that momentarily. Another tool we'll use is called BBEdit. BBEdit is a simple text editor in the Mac operating system. There are similar tools in Windows or Linux. And then finally, I'm also launching Excel, and we'll be using a file from Excel shortly. So to start this process, we have to pick a protein that we're going to bind ligands to, and then a series of ligands to bind to it. And for the purpose of this tutorial, we're going to use a human thrombin structure. The PDB ID is 2HNT. So now we're going to go to the PDB entry 2HNT. It's a human gamma thrombin. And the first thing we're going to do here is download the file. So we're just going to download the regular PDB format. And so that file is now in my system. And I'm going to shrink the screen for a moment. We're going to go to PyRX and load that molecule. So now we're loading 2HNT into PyRX, and so it's a molecule there. If I click on the Autodock tab, it's not listed in the macromolecules yet. So I go here, I right-click on this, select Autodock, make macromolecule, and it's converting it to a macromolecule. And if we go now to the Autodock tab, you can see it's in there, and it is a PDBQT file. PDBQT is a version of a PDB file that's changed in a number of ways. A computational person could give you more detail, but the simplest version of this is that it includes the hydrogens, which are necessary for docking and for binding interactions, hydrogen bonding, things like that. So now we have the macromolecule, and we need to get some ligands. So I'm going to go back to the PDB site. And if I look at the 2HNT page, I scroll down the page and I find I'm looking for the EC number. EC is enzyme commission class. And so here it is, 3.4.21.5. So I click on that, and it brings me to a page that includes a list of 793 sequence entities. So these are structures that are members of this class. 197 citations or publications associated, and what we're interested in is 337 ligands. So here are the ligands, and we want to download this list of ligands to explore it a little bit more carefully. And so what I'm going to do now is go to the Generate Reports section, and we have three options: Table View, Image Collage, and Ligand Summary Report. I'm going to select Ligand Summary Report. And we have all the ligands are shown here. There are 17 pages of ligands. I'm just going to download it as an Excel file. So there's that file, and now I'm going to actually open that file in Excel. I'm going to make it a little bigger here so we can see it more easily, and change the view so we get little bigger view. So here's a list of ligands, and if I click on a single box here, I can see this one has a fairly long name, but it includes piperidine, it includes naphthalene, it includes glutamine. So that's a derivative of an amino acid. Could be very interesting. And there are many, many structures like this in the list. But I do look through the list to find structures that I really don't care to have as ligands, like chloromethane. And so I'm just going to delete that line. And as I scroll down the list, I can find other things that I probably don't want to study in terms of docking. So here we have acetyl group, acetate ion, and acetic acid. So I'm just going to delete those three. And you could do this. I won't spend a lot of time. I do tend to take out buffers. So that's bicene, that's a buffer. We'll take that one out. Take out sugars. So there's beta-D glucose, beta-D mannose. In the case of this enzyme, this is a serine hydrolase. I don't think that the sugars really matter. I'm not going to spend any more time doing this, but you could go through, for example, and pull out metal ions, things of that sort. So I'm going to save that as ligand summary. Now, one of the things I want is I want to have all of these ligand ID values here. And so if I highlight that column and I scroll down to the end, I'm going to copy that. So that's a whole list I'm going to copy, and I'm going to open up another program. This is BBEdit. This is a simple text editor for Macintosh, and paste in those values. And as I look at this, I can see I don't really want to have that on my list because I'm going to feed these into a program on the PDB site in a moment. But I need to have them as comma-separated values. So I just do a search function here and replace the new line function with a comma. And I've gotten 329 replacements. So I'm going to select all of those, copy those, and now the next thing I'm going to do is I'm going to go to a page in the PDB to look for ligands. So I can save this and at least minimize that for the time being. I'll minimize that one as well. And here's the page I'm going to go to look for ligands. So this is a download ligand site, and you can find this just from the drop-down menu as well. And what I'm going to do now is I'm going to get that list of structures, copy that, and paste it into this box. Now I see here on the end I've got a ZN. That's zinc. I don't want that. I can see nickel. I don't want that either. So there are some things that are pretty obvious that I don't want to have on the list. So the options we're going to use here, I'm going to select individual SDF files. I'm going to select ideal coordinates from the CCD. So these are idealized coordinates, best possible structures kind of thing from the Cambridge database. And then under filtering options, I check the box for include instances with missing heavy atoms and the box for exclude atom labels from SDF files. Those are the defaults. I leave the other three alone. And then I'm going to click Launch Download Application. When I do, and if you want to download individual files, it actually downloads a program called, well, I'll bring it up in the Finder so you can see it. It's called Download RCSB. And when I go to open it, it tells me I'm not allowed to do this because it misses my security settings. These are the kind of things that we have to do in this project. I'll go back into security and I'll say open anyway. It keeps warning me not to do that. And once again it says, are you sure you want to do this? Yes, I do. And now it's asking me if I can install Java again, and I'm going to say no. Now I need to find a place to put the ligands when I get them. So I've created a folder on my desktop called ligands. I'm going to choose that one and start the download, and it's going to download all those ligands to that folder. Looks like it's going to take about 20 or 30 seconds to do that. So it's done. And if I go to my desktop and open the ligands folder, I can see that there are a lot of structures in there. I thought it would tell me the number. But in any case, they're all in there, and I'm going to leave them there for the moment. Now, what I want to do is I want to import some of those ligands to try fitting them. So I go to, in PyRX now, I go to Import, Chemical Table File. These are all SDF files that come from that ligand download from the PDB. And then I go to the folder that contains the ligands, and I highlight one that I want to load. And here it is. And I'm going to download 3 or 4 more. There are ways to download multiple files at once, but I've found them to be a little bit troubling sometimes. Okay, so we've got 4 of these structures now. Before we go any further, I'm going to show you a couple of things we need to change or settings we need to set. So if I go to I'm looking for preference. Edit preferences. One of the things we need to do is to set the number of available CPUs. Now my computer has something called double-threaded quad core. So there are 4 cores, but it actually looks like 8 to a computer. And so if I were to put 8 in here, it would tie up all of my computing power, and I wouldn't be able to do anything besides run PyRX. So I'm just going to set it to run 2 CPUs. So it'll run in the background. It'll be a little slower, but that's okay. So that's under Autodock Preferences. And if I go to Open Babel Preferences, it's going to do energy minimization. And the energy minimization, it's a force field method, and to be honest, I just know that this works. I'm not really sure what the theory is behind it. And we also use an optimization algorithm. There's either a conjugate gradient or a steepest descent, and once again, those are tools that I use without understanding completely. So I've got that setting. The next thing I do is I'm going to go in here and say minimize all. So it went through and it found the minimum energy for each of the configuration or for each of the structures. And I can click on a different structure and it will show up in the window here for all of these structures. The next thing I'm going to do is I'm going to say convert all to Autodock ligand PDB-QT. So I just did that, and so now we have 4 ligands and we have 1 macromolecule we're interested in. There's actually 2 others in there that I'm working on for a different project. But the one we'll look at today is 2-HNT. That's the human thrombin. And these are 4 ligands from structures that were in the same EC class as 2-HNT. All right. So now, at this point, we can look and see that we have, in PyRX, we have a PDB-QT version of our protein structure, 2-HNT. If I click on that, I thought it would show up in the window. It didn't. There it is, if I double-click on it. All right. And then we have each of the ligands, or each of these 4 ligands that are here. So now the next thing we're going to do is we're going to go to the VINA wizard. So this is on the bottom tab here, and start here. So the first thing we're going to do is select some molecules. So I'm just going to click the Start button, and it automatically goes to select molecules. So it has 1 ligand selected, so I'm going to select 3 more. So we have those 4 ligands selected, and then I'm going to select this macromolecule. once I've done that, I click forward and it tells me it's ready to go. If I click the button, then it will start running the optimization for each of these 4 structures. Now there are things you can change, something called the grid and so forth, but in Autodoc Vina, it's pretty autonomous. You can just hit the start button and it will run. So what's happening now is that it's actually doing the scoring function for the fitting of the first ligand. This is 1ZAL, and now it's moving on to the second ligand, Y4L, and the third ligand is running now, and finally the fourth one. And what happens while this is going on is that Autodoc Vina actually takes that ligand and tries to bind 8 different configurations of that ligand to the target protein to see how it fits. And when we're all done, we get a report that's shown down here on the bottom of the page under Analyze Results. And if we look at this, we can see 2HNT underscore ZAL. So 2HNT is the protein, ZAL is the ligand, UFF is the force field that was used to optimize the ligand, E is the minimized energy, or E equals 85.64 is the minimized energy of that ligand. And so we look in this column and we have the binding affinity. The more negative the number, the better it is. I recently watched the video by David Goodsell about Autodoc and Autodoc Vina, and in there he pointed out that the estimate for binding affinity is probably good plus or minus 2 to 3 kilocalories per mole. So if that's true, then these numbers statistically aren't different from each other. But we can see that the ZAL binds the best affinity as negative 5.3. If we scroll down to the next ligand, which is Y4L, the best binding affinity there is negative 6.1. We go to WCE, and the lowest number, the best binding affinity, is minus 5.5. This is kilocalories per mole. You can convert this to micromolar or millimolar if you wish. And then finally, the last ligand is VLT with a ligand binding strength of negative 5.9. So I'm going to go back to the top of the list, and well, let's look at the one that's minus 6.1. So this is the best binding affinity. Now, what happens when I click on that is it actually has an impact on this structure. And I'm going to zoom into the structure so we can see the ligand. So there is our ligand that's bound in the structure. The ligand is shown as sticks, and the structure is, the ligand is shown as heavier weight sticks, and the structure is shown as very narrow sticks. All I'm going to show you here is if I click on another version of Y4L, you can see that the position of the ligand has moved slightly. So that's a different conformation of the ligand that was bound. And if we go from mode 1 here to mode 2, there's going to be some rotation on this part of the structure. And so on down the structure. So different shapes, the bonds that are allowed to rotate do rotate. You get a different view. And obviously looking at this, it's pretty difficult to try to figure out what part of the protein is interacting with what part of the ligand with this kind of a view. Now it's possible to see other views in PyRX. So what I'm going to do here is change the appearance of the protein from lines to a molecular surface. And this will take just a few seconds. Okay, so now we have the protein as a surface. And now I'm going to go to this ligand, Y4L, with its 6.1 or negative 6.1 binding affinity. And highlight that molecule, and you can see it. It's kind of hard to see. I'm going to zoom in a bit here. And this gives us a better feeling for the binding on the surface of the protein. Well, actually in a cavity on the surface of the protein. But it's still not a particularly good view in terms of understanding what residues are interacting with the ligand. And in order to do that, we need to move on to another program, such as PyMol or Chimera. So I'm going to show you how to do that. We start by going to the Autodoc tab in PyRX. And if you look under macromolecules, under 2-HNT, I'll expand this folder, and you can see that we've got the protein 2-HNT.pdbqt. Well, that protein is already present in the molecules window, so I'm not going to add it. If I double-clicked it, it would put another version of that up there. But what I am going to do is I'm going to take Y4L, and I'm going to double-click on that one. And when I do that, it transfers all the models for Y4L into this window. Now, if we expand the site, you can see that they're all in there at the same time. And that's not particularly useful, but for our purposes, this is actually very useful. What I can do now is I can right-click on 2-HNT and save that as a PDB file. So I'm going to save that on my desktop in a folder I've called 2-HNT ligand binding. And I need to give each file a name. So I'm going to call this, and then I'm going to save each of these ligands. Now, this is the particular model of the ligand that's bound with the binding energy. So model 1, I'll call this Y4L model 1. And then I can go down and save all of these. That's Y4L model 2, and so forth. I could save all of those at this point. And then if I open up PyMol, I'm going to open, first of all, the HNT, or 2-HNT, the protein structure. And it's right there. And now I'm going to use a feature of the ProMol plugin to change the view. So I'm just going to change that from using the EasyViz tab here. I'm going to change that from sticks to cartoons. So here we have a cartoon rendering of that structure. And now I'm going to open one of the ligand files. And Y4L model 1. And if I zoom in on that, we can see where it's actually bound to the protein. Now, I'm not going to go through the process of looking at interactions between the protein and the ligand in this tutorial. That'll probably be a subject of another tutorial. But my intention here was to show you how to get your protein and the particular form of the ligand that's bound with a particular binding energy into the same environment so that you could explore them more deeply. And so that concludes this tutorial.